Okay, so hey, I've realized that I say okay at the beginning of almost every video. So now I'm going to try to find new things to say at the beginning of every video. So let's try it again. Hey there. Let's look at electric potential energy. So I told you about uh, these three big ideas that we have: forces, fields, and then later we're going to see potential. And sort of segued into this, we're going to have electric potential energy, or U. So that's sort of where we are right now. Is where it's I would call it a subtopic, but it's really a topic that's going to lead into potential. And in fact, that's potential. That's sort of where we get the word in electric potential energy. So we know what potential energy is. Potential energy describes an object's capacity to do work. We've seen that before. If an object has the potential to do work, to have a force applied on it over a certain distance, then that object has potential energy. And because charged particles experience forces, then they have the capacity for motion. Right? If I have two charges, say a positive charge here and a positive charge here, these charges, if I hold them in place, they'll be there, but they have the potential for motion, because if I let them go, they're going to fly apart from one another because light charges repel. So they have a certain amount of energy, or potential energy. Remember, we used U for potential energy. We can do a quick sort of ad hoc derivation. Remember, the work is force times distance, and that work by the work energy theorem is the same as the energy of that system. And so that's going to be equal to K Q Q over D squared times D. And that I can cancel out that D with one of these D's, and I'm just left with KQQ over D. So that is the expression for potential energy, KQQ over D. Let me remind you of some of the equations that we had. F was equal to KQQ over D squared. E, the electric field, was KQ over D squared, and now we have a new expression for potential energy. All these equations can be dizzying. Don't worry about trying to memorize them. They're on your equation sheet. Just be familiar with them, really, to be able to interpret them. I don't really want you to memorize the equations. I just want you to see them and be able to interpret them in the way that we've been doing. So here we can have positive or negative potential energy. Two like charges, for example, have a positive work or a positive energy. You have to do positive work to bring them together. Right? Because if I'm bringing two positively charged objects together, I have to push on them because they want to repel one another. So I'm applying a force in the direction of the displacement, and so I'm doing positive work on those objects. Imagine, I have a positive particle right here. I have to push on it in this direction. Another positive particle over here, I have to push on it in this direction in order to cause a displacement in these directions. So in both of these cases, I'm doing positive work with a force that's being applied in the same direction as the displacement. If they have opposite charges, they actually do work on you because they experience an attractive force. And that means that those charges are actually, because those charges are actually doing work on you, they're actually taking energy away from the system. So we're going to say that they have a negative potential energy. Having a positive and a negative charge, say I have a positive charge here and a negative charge here, I like to think of them as two dogs. I know these don't look like dogs, but two dogs that look like they're about to fight, and their owners are holding them back because a positive and a negative charge, they want to attract to one another. And so While our displacement is in this direction, the force that you are applying is actually in that direction, that you sort of have to hold it back and let them come up close to one another. But you're doing then here negative work. Both force and energy decrease as the distance increases, though at different rates. Because force, oops, I'm sorry. Because force is proportional to 1 over d squared, whereas the energy is proportional to 1 over d. And so I have an inverse square relationship, and then I have an inverse linear relationship. When d is very large, when I say large, I just mean that the objects are really far apart, and then I can assume it's as if d has gone to infinity, that it's gotten really big. And when that happens, both u and f will go to 0. If I have two charges that are really, really far apart, then they're going to have 0 potential energy, and they're going to have 0 forces acting upon them. So if I have two positive charges here that are close together, they're going to experience big forces, and then they're also going to have a big potential energy. But if I move those two charges really far apart, that is, d has gotten really big, and if I look at that equation, say for u, kqq over d, if this value gets big, this value gets small. And the same is true for the force. So when that happens, that means that the force on these particles is effectively 0, and the potential energy is also effectively 0. Charges will move in an electric field they prefer to move in the direction of decreasing potential energy. Like a ball rolling down a hill. Right? Now we talked about this before. I like to think of a mountain, and if I have a positive charge will move in that direction. That is, I'm moving from a position of high potential energy to a position of low potential energy. Electrons, though, on the other hand, we don't really need to get into the math of why this happens, but electrons will actually do the opposite. So just sort of remember that electrons are kind of wonky, and they do the opposite of what you think. Protons move from high potential energy to low potential energy, just like things in a gravitational field. Electrons do the opposite. Charged particles in the body similarly will move from areas of high potential energy to low potential energy. That's U to low potential energy. And we'll see that when we get into the cells. Well, we're not going into the cells, but we're going to begin talking about the cells. Okay, we'll stop there. We'll pick up with potential now.